So now we're going to be looking at circular motion, and basically circular motion is any motion that is along a circular path, such as a circle. Specifically, we're focused on something called uniform circular motion, which is essentially motion on a circular path at a constant speed. And I double underline constant speed because that's just a really important part of the definition. And the reason why is we're going to I have this circle drawn right here. And we're going to be looking at the velocity and speed at various locations. So I have one right here. I guess we can start it initially here. Along this B, right, it travels this way to B, and then let's say at C, I just cut the string off with a pair of scissors. What will happen to the particle? So we're actually going to look into this. The first thing we should actually know is that velocity kind of takes on a new meaning. It's called tangential velocity. It's still a vector, but it has a very specific quality to it. It's a velocity that is tangent to the circle at a point. It's the same. There's no difference between velocity and tangential velocity. We just use the word tangential velocity in this context because it is going to be a tangent velocity. So for example, this is the tangent velocity for A, and then as we continue on, we actually run into the tangent velocity of B. So I'm going to use this tool right here. There we go. And one thing to know is that the length of this and this, otherwise known as the speed, will be the same. That's why we give the definition constant speed and not constant velocity, because the velocity is always changing, so it can't be constant, even though its size is. So that's why we give the definition as constant speed instead of velocity. So now we look at the point C, where I cut the string off, and we want to actually track what direction will it actually go. So to me, there are actually kind of three options. We have one, so let me draw it in red. We have one, it continues along the circle like normal. Two, it kind of spirals out of control like this. Maybe kind of like I picture like a car spiraling out of control. And then three is something in between, right? Something in between. Maybe does something right there. So it's some type of between these two. And to answer this question, we actually look at the tangential velocity. Because velocity basically says what direction are you headed in, if we were to draw the tangential velocity right here, that's a bit long. If we were to draw the tangential velocity, oops, that's not, let me draw this a little bit better. Probably like there, right? It tells us the direction it's headed towards. So it tells us that it's actually going to be tangent to the circle. And just like a quick review, remember that tangent to the circle, this means basically perpendicular to this radius. So if there was kind of like a dotted line here, it would be perpendicular. So it wants to keep going this way. So in other words, it's going to keep following this path, this trajectory. And let's say maybe 3 seconds later it's here, for example, right? It's going to keep going along this. It's not going to curve any sort of way. It's actually just going to keep going because of this tangential velocity that it has. It has this direction. It's pointing in this direction, no other direction. And now the second thing we want to talk about is actually the acceleration. So let me just draw another circle here. Here I have a circle, and we actually want to find the acceleration. And remember, acceleration is kind of defined to be the change in its position as time passes, or known as the derivative of velocity with respect to time. But we're going to be talking about it in a circular sense. We're just going to talk about a geometric interpretation of it, not the calculus interpretation of it, because I find the geometric one a little bit better, in my opinion. So let's say I have this vector here, and let's just take the easy ones, the horizontal and the vertical tangent stuff. So if I were to draw the tangential velocity, which we're going to keep the same convention and doing it in blue, it probably looks something like this, right? What we have to recall is that the velocity, or the acceleration, is the change in velocity, which is related to that, and it's also divided by time. But we're actually more focused on the direction component, so we can ignore time for now. So the velocity component is its final location minus its initial vector. So if I were to define this as the final and this as initial, we actually can use something called vector subtraction or vector addition, and any way you like to call it, to actually find the direction of the acceleration. So if I were to just roughly sketch the directions, it would be this minus this, and if you remember anything about vector subtraction, it's basically the same thing as the same vector plus the opposite direction it's headed towards, and we actually want to there we go. And we actually want to use the tip to tail method, where we simply move this all the way to the tail, or not the tail, the head. So we draw this, and then we draw the other vector, and then we want to add those together so we get like something from here to there. From the tail all the way to the head. Let's see. There we go. From the tail all the way to the head, something like that, right? And I guess we can just take a point in the middle and just see what happens. So if that was the case, it would look something like this. And in reality, we should actually be taking velocity things super close together, otherwise known as the limit, as this point approaches this point. So it's like, think of it like this, and we're actually doing this vector subtraction here. But I just wanted to just get a good geometric interpretation of what's happening here. Notice that the acceleration is actually pointing directly at the center. And this is always the case in UCM, or uniform circular motion. So I'm going to write it in red because of how important it is. UCM, so in UCM, acceleration, which we actually give a name for the specific type of acceleration, known as centripetal acceleration. It always points to the center. And this is an important fact, but the fact only happens at UCM. So if the speed is the constant, then acceleration will always point into the center. And basically what the acceleration does is it makes this velocity vector start curving, right? That's why it like kind of changes direction because of this acceleration. And if we go back to this scissor diagram, once we cut off the string, there's no more centripetal acceleration at that exact moment. So that's why it actually continues going on. There's no more acceleration, anything related to the radial direction is what we call it, because it's along the radius, kind of. And that means there's no centripetal acceleration, therefore it goes off tangentially. And then how's this? Is there an equation to represent this, is what we should be asking. The answer is yes. The way we denote it is AC. Notice that I'm not going to put a vector sign here because we already know what the direction is, but this equation doesn't tell us anything about direction. It actually depends on the tangential speed, tangential speed, so there's no arrow here either, divided by the radius of the circle. So this is the formula for the magnitude of centripetal acceleration. And then the direction is towards center, always at UCM. So the next question is, how does this work with dynamics, or in terms of dynamics, right? Remember that we defined Newton's second law to be the force is equal to mass times, or the net force is equal to mass times acceleration. So then we can actually find the centripetal force. So I'm going to say the sum of the centripetal force is equal to the mass times the centripetal acceleration. And we're actually going to substitute this straight in here. The net force, the centripetal net force is equal to the mass times speed squared divided by the radius. And this will be helpful when we do Newton's second law practice in the next 5 videos. We're going to be looking at this one in the 5th video, the very last of the, mini series is a good thing to call. And then the last thing we want to just talk about is just some stuff about the circle. Specifically, things that you want to track, especially with anything that involves something that repeats itself over and over and over, right? Let's say I have this particle and it transverses the circle here. Specifically what I want to see, how long does it take to take one full cycle? And that's what we call the period, right? Especially in math class, when you have like periods of signs, like when does it return back to its original position? So this is kind of like the same idea. And the way to define period is with an equation. So the period, which is capital T, is basically just simply defined as, it's defined as how much it has traveled, and it also depends on how fast it's going, right? And so then the way we actually derive it is actually using the speed definition, I guess. It's the distance traveled over time. How much has this traveled? Well, it actually traveled the circumference, which is 2 pi times whatever the radius is, and then divided by the time. So it takes this long for this whatever speed to travel this much. In other words, we can find the period, which is basically this t is what it should be representing, and then solve directly for speed. So if speed is equal to 2 pi r divided by t, t is equal to 2 pi r over v. So I'm going to actually input it there. 2 pi r divided by v. Whatever v is, remember that speed or the tangential velocity without any direction indicated. And then the next quantity is frequency. And if you've taken a chemistry course, you know a little bit about frequency. It's just how many times does it do this per second. And there's this nice relationship between period and frequency. It's just the reciprocal of the period. If you know the frequency, you can actually find the period the same way. T is equal to 1 over the frequency. So those are the last quantities we actually wanted to be talking about in centripetal or circular motion, actually. And then we're going to talk about the forces when we get to that 5th video of that mini series. So just a quick recap. We have uniform circular motion. Remember, constant speed is the most important part of this definition because of this reason. Tangential velocity always changes. And we see why it actually changes because where's the picture here? The acceleration points toward the center, so it's always changing its velocity. And then this diagram, I had the scissors here just to think about what happens when we cut it. Well, when we cut it, there's no more centripetal acceleration, so it goes off tangent to the circle. I like to kind of think of this in terms of like the solar system. If the sun were to disappear, so whatever's in the center, all the planets will just start going in tangential, whatever this direction is, whatever they end up doing in their orbit. So, and then finally we talked about dynamics, a little bit about dynamics, then we're going to talk about it more fully in a future video in this unit, which is basically this expression, and then we substitute the equation for centripetal acceleration. And then lastly we define kind of 2 important quantities that just describe something that happens in repetition, right? Since it's a circle, it's going to keep repeating its motion in the circle. So we want to describe it with a period, which is pretty much how long does it take to complete one cycle, and frequency, how many cycles can it complete in 1 second. And they're kind of related in this way. The frequency is equal to the reciprocal of the period. So that's it for circular motion. And we're going to be looking at free body diagrams in the next, with the next 5 videos. So that's it.